Okay, guys, let's go. Come on, John. Keaton Sharma.
So 2 weeks ago, this week, I was in Urbana, Illinois at the ISMS meeting, which I think many of you know. And our first speaker tonight ran that meeting for 20 years, or more than 20 years at Ohio State. And in addition to being a great spectroscopist, he's done a great service to the community by having that meeting be the thriving thing that it is. And our first speaker from Oakview Drive in Columbus, Ohio, is Terry Miller. Terry?
Okay, thank you, John. I need to share my screen. Do you see the slides? Okay. Can people see my slides now?
Yes, it's okay.
Okay, thank you. Although I would rather be at the meeting in person, I am nonetheless very pleased to be able to speak to you virtually today. And I want to thank the organizer of the symposium for giving me the opportunity to do so. I want to talk to you about some recent work we have done computationally to understand and interpret the effects of vibronic coupling in electronic spectra. On my first slide, I have listed my co-workers. Keaton Sharma is a very able postdoc who has spearheaded the theoretical effort, which has been overseen, advised, and actively participated in by our session chair, John Stanton. The experimental data that I'll be showing you either came from my laboratory or more recently from the laboratory of Jinjung Liu at the University of Louisville. My next slide shows an outline of my talk. I want to begin with an overview of the fundamentals of vibronic coupling, which I can divide into several parts. Vibronic coupling within a degenerate electronic state, traditionally called the Jahn-Teller effect. Between electronic states that are not degenerate, pseudo-Jahn-Teller effect. And because many of the molecules we look at have unpaired electron spin, we also need to include spin-orbit coupling, which I'll refer to as spin vibronic coupling. If you're interested in more details on the fundamentals, I recommend the review article that the authors of this talk published about a year ago. The second part of my talk will compare specific results of spectroscopic magnifications of vibronic coupling and computer studies of those same manifestations. That will be divided into three sections also. First of all, we'll talk about spectra with only vibronic resolution. Then we will talk about the fine structure of those bands, which is due to spin and rotational motion. And we'll end up talking about spectral line intensities. Now to talk a little bit about the fundamentals, starting with the traditional adiabatic treatment of the molecular Hamiltonian. We have nuclear kinetic energy, electronic kinetic energy, and the Coulomb interaction between the electrons and the nuclei. These last two terms are usually combined together in an electronic Hamiltonian, which is denoted He. If we write this out in matrix form, then it looks like a fairly formidable challenge to obtain the eigenfunctions and eigenvalues of that Hamiltonian. However, we can make it less formidable if we apply the Born-Oppenheimer approximation and remove the off-diagonal matrix elements of the nuclear kinetic energy. Then we can use our favorite quantum chemistry suite, which naturally is C4, to produce the eigenvalues and eigenfunctions of the He matrix, which we denote as VJJ, which is a function of the nuclear coordinates capital R, and psi j, which is a function of the electronic coordinates, lowercase r, and the nuclear coordinates. Once we have VJJ, we can combine it with the nuclear kinetic energy operator to write a Schrodinger equation for the vibrational motion. And we can obtain the vibrational eigenvalues and eigenfunctions. The total vibronic eigenvalue then is the simple sum of the electronic energy plus the vibrational energy. And the vibronic eigenfunction is a simple product of the vibrational wave function and the electronic wave function. Now, looked at from a more schematic point of view, what we're doing is we're diagonalizing the electronic Hamiltonian, eliminating these off-diagonal matrix elements. We are then adopting the Born-Oppenheimer approximation to neglect the off-diagonal matrix elements in Tn, and we're separately solving the vibrational problem. Usually, the Born-Oppenheimer approximation is adequate. Otherwise, quantum chemistry programs would not be nearly as successful as they are today. But there are certainly cases where it's not sufficient. For example, if the energies of the states between which you're neglecting the nuclear kinetic energy coupling become degenerate or nearly so. And what we're going to be talking about today is handling cases like that. My next slide shows one possible way in which we could try to do that, and that is we can make these off-diagonal matrix elements rigorously zero by adopting an electronic basis set, which consists of functions for which the nuclear coordinates are fixed at R0. Well, that does take care of the nuclear kinetic energy, but the electronic kinetic energy will certainly not be diagonal, and it may be a challenge to diagonalize it in terms of this basis set. Even if we could do that, we would lose the concept of a potential energy surface. So usually the truly diabatic picture is not a practical way of proceeding, but a quasi-diabatic basis is. In that case, the electronic states are chosen such that they evolve slowly with nuclear position. So these off-diagonal matrix elements are justifiably small and negligible. The electronic Hamiltonian is still not diagonal, but with this basis, it is more simpler to make it so. However, in this basis, the molecular Hamiltonian must be projected on basis functions that are products of electronic and vibrational spin wave functions. We look at that in a little bit more detail mathematically. We have a Hamiltonian here that looks similar to the one that we had in the adiabatic case, except that the off-diagonal zeros are more justified. And the details of the V matrix elements here are considerably different than they were previously for HE. Definition here shows that they are matrix elements HE between these product wave functions of vibration and electronic. This can be expanded in terms of a power series in the normal coordinates Q1 to QP, and one can truncate it at whatever value you want to, as indicated there. The eigenvalues can then be obtained from that matrix, and the eigenfunctions likewise. And now they will be linear combinations of products of vibrational and electronic functions. The important thing here is if the matrix can be considered, or the matrix can be considered as an expansion which consists of parameters that depend upon the electronic Hamiltonian and these normal coordinates. We can then correspondingly write that in the quadratic case as follows. This is the standard quadratic vibronic Hamiltonian that's been used for years with respect to doubly degenerate electronic states. First of all, we have the standard harmonic oscillator term, and then we have several terms that are labeled Jahn-Teller. This is the linear Jahn-Teller, linear in the normal coordinate. These others are quadratic in the normal coordinate, and they're distinguished by the particular components that the bilinear combination is composed of. If we are dealing with a molecule with unpaired spin, we need to add spin-orbit coupling. And then we need to obtain the eigenvalues and eigenfunctions of this matrix. Fortunately, we have two programs that can do that. The socket program written in my laboratory, and in using normal coordinates in cylindrical, expanding normal coordinates in terms of cylindrical coordinates, and XSIM written in John's laboratory using Cartesian coordinates. This now sort of gives you the overview of the vibronic coupling. And so for the rest of my talk, I'm interested in comparing specific results from individual spectra observed experimentally with computations on those spectra. And the first thing I want to do is I want to look at spectra which show vibronic resolution only. And for those, we'll simply need the vibronic eigenvalues. An example of such a spectrum is the photoelectron spectrum of CH3O-, which was taken in Dan Newmark's group. And this shows the portion of that spectrum that corresponds to the ground electronic state of the methoxy radical CH3O. In a collaboration, John Stanton performed simulations on that spectrum, which are indicated by the red sticks. In the top trace here, he only used the linear Jahn-Teller term in that previous slide. And as you can see, he's able to reproduce the general features of the spectrum, but the details leave something to be desired. One thing is that there's no doubling of these components. And if you put in spin-orbit coupling, as he did in the lower trace, then you see that these are a result of spin-orbit splitting. And you can see a much better agreement, but still certainly less than perfect here on the higher energy vibrational structure. In my next slide, I'm going to cut out this blank section in the middle so that I can show these two sections in more detail. And now the blue bars correspond to the previous calculation on the bottom trace. And the red bars are generated by including with that previous Hamiltonian also quadratic Jahn-Teller effects and cubic and quartic terms in the non-Jahn-Teller part of the potential expansion. Now you see rather good agreement. Certainly the origin region here is in good agreement between experiment and calculation. And if we look at the higher energy region, we see that one predicts rather accurately the positions of the stronger vibrational levels. Nicely, one sees the prediction show a dramatic quenching of the spin orbit splitting in these levels compared to the origin band. So one can see that in general now one has a situation where the calculation and the experiment are consistent with one another. So now I want to go and talk about the fine structure of such vibronic levels. And I'll show you a spectrum, once again, of CH3O, but now this is a laser-induced fluorescence spectrum of methoxy, which is from the which is the origin band of the transition from the ground degenerate state to the excited non-degenerate state. These are some 100 or 200 rotationally resolved transitions. And at that time, when we took the spectra nearly 30 years ago, we also showed a simulation of that spectrum, which we referred to as calculated. However, calculation didn't mean the same thing 30 years ago as what I've been talking about today. Calculated then meant that we took an effective Hamiltonian, which contained all the symmetry allowed fine structure terms, and which were then parameterized, and we fit those parameters. And after we fit the parameters, we used that those results to simulate the spectrum, in fact, within experimental error. In this particular case, we used over a dozen parameters in our fit, but as I said, we had a couple of hundred lines to fit, and so we got well-defined, statistically well-defined values for them. I'm not going to talk to you about 12 different parameters. I'm going to select 2 parameters from the rotational Hamiltonian, which are called H1 and H2. And H1 and H2 would be 0 if there are no vibronic effects in the spectrum. And I will tell you that we got non-zero values for H1 and H2 when we fit this spectrum. Now, what about calculating H1 and H2? Well, here's a slide which is fairly heavy mathematically, and so I'm just going to try to hit the high points. And basically, it begins by showing that all fine structure interactions can be written in the form of a parameter, which we call O here, which is determined by the vibronic eigenfunctions, and then is multiplied by a bilinear product of components of P and Q, where P and Q are components of an angular momentum, either the spin angular momentum, the rotational angular momentum, or the vibronic angular momentum. The 0th order term, when we expand the parameter O, corresponds simply to the standard symmetric top Hamiltonian for a C3V molecule, which we've indicated right here. But if we go and look at the linear term in the expansion, then we find the parameters H1 and H2. And as I said, if there were no Jahn-Teller distortion of the molecule, H1 and H2 would be 0. However, most importantly, this formulation shows us how we can calculate H1 and H2 in terms of these derivatives of the rotational constant tensor. So now let's see how what we're able to do when we try to compare the experimental results and our new calculation. Well, experimentally, we found that H1 was 75 megahertz and H2 was 1331 megahertz. Our calculation 3 years ago was H1 76 megahertz and H2 1268 megahertz. I think this is actually rather remarkable agreement. Now, there are not too many places where there is experimental data with which to compare with calculations like this, but one other place where there is the ground state of the cyclopentadienyl molecule, which is also doubly degenerate, and whose rotationally resolved spectrum is shown at the bottom trace here in green. We did a fit to these rotational transitions using a Hamiltonian equivalent to the one I just showed you. And then with the fit parameters, simulated the spectrum. And as you can see, once again, we get a very good agreement. And the value of H1 that comes out of that is 212 megahertz. H2 is, in this case, is equal to 0 because of the planar symmetry of the molecule. When we do the calculation now, about 30 years later, we find a value of 207.1 megahertz. I will tell you that if somebody would have asked me whether it was possible to calculate values for H1 and H2 that were comparable in accuracy to the experimental values that we had determined 30 years ago, I would have told them that there was no way that was going to happen. But obviously, this result shows that it did happen. So now I'd like to finish up by talking a little bit about spectral line intensities. Actually, the effect of vibrational coupling on line intensities is a relatively old topic, as illustrated by the early paper of Hertzberg and Teller in 1933, but is given contemporary relevance by efforts to laser cool molecules these days. So I want to talk just a little bit about laser cooling of molecules. First of all, the principles of laser cooling, I think, are probably known by most of the people in the audience. But basically, the idea is that if you have a molecule and a counter-propagating photon, the molecule can absorb the energy of the photon and be placed in an excited state, but it will also have its momentum reduced by the momentum of the photon. And so after the fact, its velocity will be lower than it was before. And if you do this enough times, then you can keep slowing the molecule down until it reaches a quite cold temperature. The question is, how many photons have to be absorbed for this to happen? To give you a little perspective, for a typical molecule and photon energy, it requires something like 10 to the 5th photon to reach millikelvin type temperatures. Now, laser cooling of atoms have been going on for a couple of decades now with a great deal of success. And in the last few years, there's been interest in cooling molecules, principally because in some cases, even though the molecules are probably certainly more difficult to cool, they may be better than cold atoms for the application of the experiment. Now, what kind of reasons are you going to cool atoms or molecules? Well, one thing is discovering new physics beyond the standard model, ultra-cold chemistry, quantum computing. We'll focus on new physics and ask ourselves the question, what kind of molecules would be useful to consider for those experiments? And the answer is, first of all, ones that are sensitive to new physics. And in many cases, there are reasons why molecules are more sensitive to new physics than atoms. The other thing is they're going to have to be good candidates for laser cooling. And that requires a large oscillator strength so that we can absorb something like 10 to the 5th photons. And we also have to have an absence or a small number of transitions to intermediate dark states where the atoms can be lost to the cooling cycle. Well, how does this translate to the actual molecules? Well, candidates that have been suggested include certainly the metal alkoxide, MOR, M being 2A or 2B metal, and R being an alkoxy group. And in fact, the molecule that has attracted the most interest recently is the calcium methoxide molecule. In fact, it is the only nonlinear polyatomic molecule that thus far has been laser cooled. I don't want to talk to you about laser cooling of calcium monoxide, but I do want to talk to you about the spectroscopy of the transition which has been used for laser cooling, and the spectroscopy is indeed relevant to that laser cooling. Here is a spectrum of calcium methoxide. On the top trace was taken in Jin Zheng's laboratory at the University of Louisville, and it's at about 10 degrees Kelvin, and it has vibronic resolution. Now, one thing I should tell you about this particular trace to begin with, since we're talking about intensities, is that the two strongest lines here corresponding to the vibronic for origin band are optically saturated. And so in an independent experiment, it was determined that they should be multiplied by a factor of 3.6. So this origin band contains greater than 90% of the oscillator strength of the electronic transition. But if you're going to want to do 10 to the fifth cycles of photon absorption, then you still have to worry in detail about the remaining 5 to 10% of the oscillator strength. And so first of all, we're going to analyze this vibronic structure in the same way we analyzed the vibronic structure in the methoxy radical spectrum from the photoelectron experiment. And the thing that we noticed to begin with is that it consists of doublets, where our simulated spectrum down here are single lines, but that simply means that we have to take into account spin orbit splitting. Experimentally, the spin orbit splitting is 67 wave numbers for all of these transitions. And if we calculate the spin orbit splitting, we get a value that's the same within a couple of wave numbers. And so we see that our predictions down here are right in the center of these doublets. And so certainly we have a good match to the positions of the vibronic levels in the A doublet E state. Now we can also assign the allowed transitions in the entire spectrum. And those transitions have to end in totally symmetric vibrational levels. And you can see that all of them do, except for this transition right here. We can look further in the table that we have created from our calculations for vibrational frequencies to see if we can possibly come up with an assignment. And in fact, we can find one relatively easily. This corresponds to the fundamental mode 8 in the molecule. And mode 8 is a doubly degenerate bending motion in and out of the plane of the CaOC bond, and is of E symmetry, which means its fundamental transition is forbidden in the absence of vibronic coupling. Well, clearly it's there, and we are interested in understanding why it's there and why it has the intensity that it does have. There's a particular reason why we're interested in this, and that is there was a paper published about 5 years ago in PhysRev Letters that argued that degenerate vibrational doublets like this would be particularly sensitive to violations of parity and time reversal symmetry. So it's a very sensitive molecule for looking for new physics. So now let's look at calculations. Calcium methoxy has 3 electronic states. The ground non-degenerate. First excited state is a doubly degenerate state, and then nearby it is a second excited electronic state. This is the simple adiabatic approximation matrix that one is already diagonal. And if we use this matrix, we will see, inconsistent with the spectroscopic selection rules, that there is no intensity predicted for this transition. On the other hand, experimentally, it carries about 2.8% of the oscillator strength. And interestingly, unlike the other doublets, both of the spin components are not equally as intense. They have a ratio of about 2.7. Well, now, if we consider some other terms in our Hamiltonian, we try to add spin orbit coupling along the diagonal of the A state. We certainly change the shape of the potential, but we don't affect the calculated value here of the intensity. Well, I mentioned that there could be spin orbit coupling, Jahn-Teller coupling in this state. And indeed, when we include that in our calculations, we do get a non-zero value, but one that's an order of magnitude too small. If we include pseudo-Jahn-Teller coupling between the A and the B state, we increase this value by about 50%, but still it's much smaller than the experimental one. The key seems to be to include spin orbit coupling between the B and the A state. In that case, one certainly gets a reasonably close agreement between calculation and experiment. And most importantly, we notice that the ratio is approximately correctly predicted between the two spin split components. We've done some work on the asymmetric species. I do not have time to talk about that, but I will just indicate that we have published a couple papers recently on that. And so I want to wrap up, have a short summary of the high points that I think establish the integration and usefulness of combining electronic structure calculations and experimental results. But I think the real take-home message is from the aggregation of these points, and that is that modern quantum chemistry approaches can produce quantitatively useful results for the assignment, analysis, and understanding of the spectra of molecules that exhibit vibronic coupling effects that are not well described by traditional adiabatic Born-Oppenheimer approach. There's still work to be done. There's a few things specifically to be done theoretically and experimentally, but I think that the foundation has now been well set. And at that point, I want to thank you for your attention.
Thank you, Terry. We have time for questions. Jonathan?
Hi, Terry. Jonathan Tennyson here. Thanks very much for that. Can you tell me what you do about the Berry phase in your degenerate states?
What we do about the Berry phase?
How do you treat the Berry phase in your degenerate states?
The degenerate, the Berry phase is what happens when you have an electronic wave function and you translate it through a circle about the conical intersection, which should take you back to the same electronic wave function, but it doesn't in this case. You have to go around 4 pi. But that does not enter into the vibronic matrices, which we calculate and diagonalize with socket and XSIM.
Approximation, or does it rigorously not enter in?
I don't think it's an approximation.
Josh.
Hello. Hi, Terry. Josh Baraban.
Hello,
A
Josh.
quick question. So you talked about these H1 and H2 parameters and how these can be calculated accurately now. Is it possible to calculate all of the parameters in the Hamiltonian, the vibronic Hamiltonian that you described ab initio, or is that not yet established?
Well, if you look closely at the slide, you'll see that the one of the things left to do for future work is to do similar calculations on the spin-dependent terms, like spin rotation, and if you have a triplet state or higher, spin-spin interactions.
Okay, thank you.
Again, for a great talk. Our next speaker is Klaus Müller-Detlefs from Manchester.
Of something which is actually quite intriguing, which is a periodic many-body system observed in a molecular quantum degenerate plasma. So first let's have a look, how do we make the plasma? We use a molecule which a lot of you will know is nitric oxide. This nitric oxide we expand in a supersonic jet with neon, and then we use two lasers to first excite the rotational ground state in the J1/2 negative parity level into the intermediate A state, which then is rotationless. And then we have a second laser to excite the molecules very close to the ionization threshold, just a couple of wave numbers below the ionization energy. And then what we observe, because we are exciting the system very close to the nozzle of the supersonic jet, so we have very high density. Then when we scan this second laser, omega 2, around the ionization threshold, then we observe Rydberg states very much below the threshold. In fact, we observe two series, the F series, which is long-lived, and the P series, which is very short-lived. So we observe the F series down to, in this case, down to 22, and the P series even down to 24. So this is this is done at very high density of approximately 10 to the 16 per cubic centimeter. If you do this experiment in a skimmed molecular beam, such as in Ed Grant's group, then you see only the F series and only down to approximately n equals 41. And this is in this insert. And you also don't observe anything above the threshold and no low ends. I should also say there are two thresholds here. The F series converges to n plus equal 2 and the P series to n plus equal 0. So how do we measure something from our plasma? We have a time-of-flight system with a collinear supersonic jet expansion. So we have two lasers which are actually in opposite direction, and they excite about 1 to 2 millimeters away from the nozzle. And then what we do is we first generate a plasma in this position. And then according to the velocity, which is well known for a neon expansion, is say after 100 microseconds, the plasma will be around this position. And then if we wait 300 microseconds, it will have reached the first plate aperture in the apparatus, which is a large gold-plated plate with a 5 millimeter diameter hole. And then we apply a high voltage pulse to this aperture, which then will push anything that will be there and is positively charged onto our microchannel plate, which can only detect positive charges. So let's have a look what would happen. So in order to detect these, the plasma has to actually be at this plate 1. But then we discovered that actually if we use a much longer pulse of 3.6 kilovolts onto aperture 1, the pulse has to be around 6 microseconds, then we observe another signal, and that means now when this pulse fires, actually the plasma cannot yet have arrived at the plate. So this is the first intriguing observation. So then let's see how does this look like. It's a diagram which tells us the time of flight which is observed, then on this axis, and also the delay of this pulse 1 with respect to the laser firing. So the first signal that we observed was mainly for a delay around 300 microseconds. This we have used, for example, to scan the laser to obtain this signal which showed us the Rydberg states. But as you can see here, at a delay around 170 microseconds, there is another signal which is very broad and actually roughly saying it's 4 broad peaks in a very broad chunk of signal, and also at a different time of flight. So then we thought, let's play around with this. So somehow, when we apply the first pulse, something must have arrived at aperture 1. Then the pulse ejects something into this direction. So let's see what we can do with the second pulse on this plate 2, which is actually a grid. So we are now firing a second pulse, which is only 1.2 kilovolts. The first pulse is still 3.6. And then we scan the delay between pulse 1 and pulse 2. This is why we call it the P1, P2 experiment. So how does that look like? So this is a little video. So our pulse 1 is 3.6 kilovolts, fired at 180 microseconds after the laser shot. The pulse 2 is a third of this voltage, and now we have the delay between pulse 2 and pulse 1, and we start at 2.5 microseconds, and this number will now change, hopefully, if I can actually switch on this video. Okay. Okay. Click on the red dot.
Just click.
Okay. Click next one. Okay, no, it hasn't started. One more. Here we are. Okay. So you see something is happening here. Around 3 microseconds, suddenly very sharp peaks appear. And if I stop this here, so there are essentially 14 very sharp peaks. And, okay, no. Okay, so there are, so can I stop this by pressing the button or? Okay. So, very good. Okay. So we have 14 very sharp peaks in this time of flight mass spectrometer, and their width is about 2 nanoseconds in a linear system. So that's something which one would normally not observe. So this signal is always, from day to day, 100% reproducible. So now we have to find out what is the situation with this, how can we understand this one. And the first thing is to understand how can we observe something which is positively charged when the plasma, when we start it, is actually neutral, essentially neutral. So we have a long pulse on this aperture 1, and fired at 180 microseconds. Then what happens is the plasma is separated into a negatively and positively charged cloud. How can this happen? The field doesn't penetrate into the plasma, but it will interact with the outer electron sheath, and actually this means the electrons will be polarized, and then actually the electrons will pull at the ions inside, and they will actually lead to an elongation of this plasma with a negative part propagating towards aperture 1 and the positive part propagating into the other side. So then when this negatively charged part actually comes in contact with aperture 1, electrons will flow out of this negatively charged, and you will generate a charge inversion. So now you have the positively charged part on this aperture 1, and then this will be actually, these positive charges will be accelerated towards aperture 2, which, for example, can be grounded, or where you can have another potential which then will lead to a defined potential energy difference between 1 and 2, and a defined acceleration towards the detector. Okay, so now we thought this is 1-2 experiment is a bit complicated. Can we do it much easier? And we found a way by actually using only one pulse generator, by actually generating a double pulse. So what we do here is we have a pulse with a gap. The first length of the pulse is 5.5 microseconds. Then we have a gap of 100 nanoseconds. And then we have a long pulse. The length of this actually doesn't matter. So we have again the same situation. The plasma is here about 13 centimeters away from aperture 1. We fire our first pulse. Then after 5.5 microseconds, we have the gap. So the difference is now there is a phase connection between this pulse falling down and this pulse coming up. And this because this rise time is below 20 nanoseconds, and it's very, very precisely maintained. So that this now slices up the plasma, and and the difference is now that actually the peaks that before were broad turn out to become very sharp, and you get exactly the same structure as we had in the first pulse 2, pulse 1 experiment. And if we look at these in a much more sort of now as a single spectrum, then anybody who has some experience with the time of flight spectrum, where the time of flight is proportional to the root of the mass to charge ratio. So we are not able to determine the mass directly, we determine the mass to charge ratio. And then one would immediately see that actually the distance between these different peaks, which actually becomes smaller from the left to the right, corresponds to a constant change of mass to charge ratio. And if we just do this analysis in terms of the mass to charge ratio of NO+, which is 30, then we see the first peak has a mass to charge ratio of 35, then 37.5, etc. So that's quite striking, because that doesn't fit any sort of like a molecule or cluster which is in non-covalently bound cluster in the system. Also, we find if we take actually the mass to charge ratio of NO as 30, and take this, define this as 1, then our first mass to charge ratio is 7/6, and by increments of 1/6, it goes up to 3 and above. So the other thing we can do is, are there any peaks that we think may be missing? We can add this progression. These are the red lines. And in fact, some of these peaks are not all missing, but this is a discussion something that one needs to do later. So essentially, we have a progression. This fits perfectly well, a progression of mass to charge ratio. And here we're writing this down once more. And so if we keep it to the NO mass to charge ratio, it goes 35, 37.5. So the increment is actually 2.5 exactly. And now if we express it as MNO equal 1, then I start with a ratio of 28 over 24. I've made these all as even numbers. So this would mean I have 28 ions, but only 24 charges. Okay, now it is more convenient to actually reduce this to the ion-electron ratio. So in this case, the first one will be 28 ions bound by 4 electrons. The next one, 30 ions bound by 6 electrons. This one, 58 ions bound by 34 electrons. So let's now see how this can emerge. So first, we elongate the plasma. We get the negatively charged part touching this plate number 1. And then this becomes positively charged, and from this elongated plasma, then we apply our fields to get the slices, and these slices, they are now moving in this direction. I've indicated here like these 14 slices. They can be further interrogated by applying another pulse on this grid 3, but I'm not showing this. But we have done that, and that confirms everything that we observed. So there is something like a fractional quantization, which is very intriguing. So let's wind this up. So the expansion of a plasma without field is essentially governed by the residual temperature of the ions in the supersonic jet. That's about 0.1 Kelvin. So the plasma itself is widening up very slowly. However, when you put an electric field, you produce plasma elongation because as the electrons are moving on the surface, and then this negatively charged cloud pulls at the ions, which are also moved. That means the whole plasma actually is elongated. When this negatively charged cloud actually contacts the high voltagely biased aperture plate, you form a positively charged cloud, which is trapped at the aperture, and then when you switch the high voltage applied to the plate off and after a gap on again, a set of planar positively charged objects is produced that shows periodicity in their respective ion-electron ratios. So this double pulse produces a phase correlation, and which is not there in the first place. So in the first place, we think this is textbook physics, that when you start with a disordered statistical distribution, you provide a neutralizing electron background, then you form essentially an ion crystal, Wigner-Abrikosov ion crystals. So that's standard textbook physics. So now the question, how can we do anything about this fractional charge? So for example, here we could have 28 ions, 4 electrons. So it's essentially 7n ions bound by n electrons. This is very striking. How is this possible? 11n ions bound by 5n electrons, 3n ions bound by n electrons. So this may be something like a fractional quantization, but this observation is there, and so there could be some connection of understanding, but this is not proven yet. The most important thing is we can say what this signal is not. It doesn't come from molecular clusters, from any other interactions. It's really objects that lose electrons, and they have a very high ratio of ions to electrons. And with that, thanks to François Michels for leading the work.
Any questions? Does this have any potential application to quantum information?
I'm pretty sure. I mean, essentially what yes, sorry. Essentially what I think, but of course it's not proven, is this is in a way a many-body quantum matter, and so with which you could do lots of things. And because it's not really conceivable that, say, normally you would not say, okay, I have, say, 7 ions bound by 1 electron. I mean, that's not really, but in the system, these have now, instead of, say, 1 Bohr radius approximately distance, like in a molecule, but they have, say, a few hundred or 1,000 Bohr radius difference. So the Coulomb repulsion between the ions is considerably smaller. And of course, you could delocalize the electron or the electrons between the ions so that actually you get something stable. And also we think there is a residual, very long plasma cylinder in the center on which these objects could glide, but this is pure speculation at the moment. Okay.
Speaker is Stéphane Cousin from CNRS.
Okay, thank you. So I will speak about the UV photochemistry of acetylacetaldehyde trapped in 4 cryogenic matrices, but more than acetylacetaldehyde. What I would like to present, in fact, this is a trilogy, because as you can see on this slide here, as you can see here, acetylacetaldehyde is like the 2 other molecules, malonaldehyde and acetylacetone. They're the most simple molecules which exhibit an intramolecular H bond here and an intramolecular potential proton transfer. So malonaldehyde here presents here 2 hydrogens, while acetylacetone has 2 methyl groups here, and of course acetylacetaldehyde is a hybrid form with 1 methyl on the OH side. I will call it OH form, and on the CO side here, and I will call it CO side, okay? So it has been characterized theoretically and experimentally that after UV absorption, malonaldehyde proceeds through uniquely singlet states to come back to the ground state or to isomerize, while acetylacetone here proceeds to triplet states, uniquely triplet states. And it has been postulated that it came from the fact, from the coupling, the weak coupling between the 2 rotating methyl here. So that was the right occasion here to see if this coupling was really responsible for this triplet state UV relaxation. So the first goal you have to do when you trap these kind of molecules into a cryogenic matrix, so after deposition, it exists uniquely this enol form here because of these really strong hydrogen bonds. So in our case, we did not observe the keto form, we just observed the enol form. And upon UV radiations, you can create all these isomers here by rotation around all these bonds. And in acetylacetaldehyde, we observed all those isomers here, the 6th one here, but we did not observe this one. It's easy to understand because if you consider here the electronic repulsion between the 3 electrons and the fact this bond here, the CC bond here, is really poor electronically speaking, it's really easy to spin around this bond. So we did not observe this one. But it's not the most important here to identify these isomers. The most important is to understand if these isomerization are proceeding through triplet or singlet states. So here I present a summary of what happens concerning acetylacetone in gas phase. It has been proposed by Jean-Michel Mesdag in 2007. So we have the chelated forms because even in molecular beam, the enol form is predominant, okay? So after the laser pumping, there is a transition between S0 and S2. There is a departure from the Frank-Condon region in 50 femtoseconds. And then there is a relaxation through S1 here. And at this point here, there's a triple a triple conical intersection between S1, T2, and T1. So if you're in matrix here, the cage effect will prevent any dissociation, while in gas phase, you will observe this dissociation, okay? So in matrices, the conclusion of our works was that for acetylacetone in gas phase, there is a dissociation of the enol form, while in matrix, the main UV relaxation process is isomerization. And even we're not time resolved, we're not working with step scan spectrophotometer, even we're in matrix, with simple experiments, we're able to suggest this global overview of the mechanism, the UV photoreactivity of acetylacetone, with here the chelated forms, transition between S0 and S2, and then you can go back through T1 state toward the ground state here, or to induce isomerization. Or you can have, of course, fragmentation through Norrish-1 reactions, and this is the same for the chelated forms. So matrices, they're quite simple to carry out experiments in matrices, but you have to accumulate a lot of matrices in order to retrieve some information. But even you're not time resolved, you're able to suggest this kind of summary. Of course, other team did some calculations. So Chen and coworker, they did calculation on these systems, and here they illustrate the isomerization between this TCC form toward the CCT form. One more time, we observe here a transition between S0 and S2, then a relaxation through S2, then S1, and there is this triple intersection here, and then you can go back, you can have isomerization in T1, can go back here to the ground state, or you can observe fragmentations. So in fact, experiments and theory are telling the same story, fortunately. Concerning malonaldehyde, this is another story, as I told you. This is purely singlet. So this is a theory, this is a theoretical model provided by coworker, and we see that after one more time transition between S0 and S2, there is a conical intersection, and then we come back without radiation toward the ground state with or without isomerization. So carrying out experiments in cryogenic matrices, we observed the same phenomenon. We did observe a purely singlet relaxation for malonaldehyde. So the method, I won't be long on it because as you have heard a lot about, so here this is the experimental device with the cryogenic head, and here the sample carrier. So the main diagnostics are FTIR spectroscopy and UV spectroscopy, and typically we use our mercury lamp, a really classical mercury lamp, or tunable laser here, located behind this wall. And typically we couple these experiments with theoretical methods, so typically semi-empirical or ab initio and DFT calculations. So this is really simple, and many groups are doing the same in the world. So what about how to detect finally a triplet state in matrix? So you can use two effects, or you detect a heavy atom effect weighting down the matrix from neon to xenon, because a heavy atom effect will favors an intersystem crossing. So if you're interested in the kinetics of the displacement of the parent molecule, you will see between neon and xenon an acceleration of this dispersion. Or you try to observe a quenching effect by the deoxygen. But deoxygen is able to quench singlet states, triplet states, and is able to catalyze intersystem crossing. So one more time, you have to think about, this is not a really simple reaction you're going to study. So here are the UV spectra recorded in argon and neon. So after deposition, this is the blue spectra here, the same in nitrogen. So they're quite similar. And as I told you, because we're at 4K, the proton is located, and we observed the two forms of the chelated form, so the CO form and the OH form. So they're located here and here. But after deposition here, we observe also other bands, and these bands are due to water impurities. So with water impurities, you will have also in the matrix, you will have mixed dimers between acetylacetaldehyde and water. And of course, irradiating with the broadband irradiation, you have the parent molecule is isomerized, and then you observe mainly here, this is the non-chelated OH form, and here, these are the non-chelated CO form. So now, if you have a look to the IR spectra, because this is with IR spectra that we're able to identify which isomers are present in the matrix. Here on this side, this is the COCC stretching region. This is with O2, and here this is without O2. And we knew from our past experiments with acetylacetone that in this region here, between the two dashed lines, if there is a fragmentation, we should observe fragments in this region. And what do we see here? It's obvious that mainly in neon and in xenon, we observe fragments, okay, in presence of oxygen, while without oxygen, it's quite clear, except in xenon. While in argon and nitrogen, we observe fragments, but it seems to be a little bit less clear. And together with fragments, we observe CO, and in neon, we observe also CO2 here, so this is with oxygen and without oxygen, so we observe here CO2 formation. So obviously, with O2, there is not what we can call a triplet quenching. There is a reaction because O2 can be written as T0 or S2, and O2 is an electron scavenger. So as soon as O2 is in presence of radicals, there will be a reaction. So we saw nothing on the kinetic constants, so we did see no heavy atom effects. And doping the matrix with O2, we didn't see effect on the kinetic constants, but we see here that we increase the fragmentation of acetylacetaldehyde. But which isomer? The chelated ones, like in the gas phase, or the non-chelated ones? So to answer this question, we used, in fact, interferential filters on the chelated forms here at 266, and on the non-chelated forms here at 222 nanometers. And obviously, one more time, we should observe fragment in this area. And using those filters, we observed even those experiments that have been done with deoxygen. We observed no fragmentation with these filters. So in fact, there is no fragmentation upon UV radiation on pi-pi star transition of CCC. This is the case here. There is no fragmentation. But this is also the case when we radiate on the non-chelated, mainly CO form. There is no fragmentation. So the conclusion is that there is a fragmentation in the matrix, but it comes from n-pi star transition of the non-chelated forms. And we're sure of it because this fragmentation starts when the parent molecule, the chelated forms, are quite disappeared. So contrary to what we observed in the gas phase, this is not the chelated forms which dissociate in cryogenic matrices. This is the non-chelated forms. And this is exactly the same story as what we saw for acetylacetone. So obviously, this is not the coupling between the two methyl which induces, in fact, this dissociation of non-chelated forms. It comes from the fact there is one methyl on this pseudocycle. So we have the end of the story, because here, as I said, malonaldehyde is purely UV relaxation process, while for acetylacetone and acetaldehyde, the UV relaxation pathway is a triplet relaxation pathway. And contrary to what we observed in the gas phase, in gas phase, those chelated forms here fragmented, while in cryogenic matrices, this is the non-chelated forms which are fragmentating. Of course, this is a really brief summary of years of experiments, calculations, selective irradiations, and many people have been involved in this work, so namely Aurélien Trivellin, Karine Manca, Francis Marinelli, Nicolas Ferré, and Pierre Rousselot-Paillet from Aix-Marseille University, Tobias Wassermann and Nils Litzwager from Georg August Universität in Göttingen from Martin's group, and Joël Massetti, Christian Aupetit, and Sophie Soborska from Bordeaux University. By the way, today this is the birthday of Joël, so happy birthday, Joël. Thank you for your attention.
We have questions? Anyone?
Thank you for the talk, Eric Heller from ETH Zurich. So I have a question regarding the simulations, because these triple conical intersections seem very complicated. It seems like there would be a lot of decoherence and recoherences going on. So I was wondering, how did this group tackle this issue? Which dynamics method did they run?
I can assure you, you will have to read this paper, because that was a long time ago, and we did not collaborate with them. They published at the same time as us, and we were really happy to see that the mechanism they have suggested was almost the same as the one we suggested, but in fact, I don't remember precisely what is all the story. They discussed about this conical intersection, but that was far from my knowing concerning the theoretical chemistry, really. Sorry.
No worries. I was just wondering, because often people use surface hopping for these kind of things, but of course there you would have a massive overcoherence problem, especially if you have a triple conical intersection.
In fact, the malonaldehyde is one of the favorite molecules of physicists because of this proton transfer. So if we consider the amount of theoretical articles compared to experimental articles, it's more than 100 to 1, something like this. So there's a battle about the transition state of this between when the proton is oscillating between the two oxygens, and there's a battle also about these conical intersections. They're really complicated papers, but I must say that it's a battle between theoreticians, so it's a bit complicated.
Okay. Thank you.
Other questions? If not, let's thank our speaker. The next contribution is a remote talk by David Anderson from the University of Wyoming.
I'm very thankful for the opportunity to talk today about some work going on in my lab virtually. So we study molecules trapped in parahydrogen solids. And so what I'm showing here is the output of a quantum Monte Carlo calculation done by my collaborator, Professor Robert Hindi at the University of Tennessee, where he was modeling N2O in a solid parahydrogen matrix. And the beauty about solid parahydrogen is shown in this figure is that the parahydrogen molecules are not located, how'd that happen? Are not located precisely at their lattice positions, but they execute large amplitude vibrational motion within the lattice. And that's what's shown by these sort of shotgun marks, yeah, of the quantum Monte Carlo. And what this means is that within the solid, two neighboring parahydrogen molecules, their wave functions overlap. And this overlap of the wave function can lead to exchange. And this is the mechanism basically by which impurities can become delocalized within the parahydrogen solid. And those are the types of things that we're currently interested in and are trying to study. So the delocalization of hydrogen atom impurities in solid parahydrogen has been known for a long time, along with HD and orthohydrogen. But in 2003, Fushitani and Momose did an interesting study, in my opinion, where they looked at the chemical reaction between H and nitric acid, or NO, excuse me. And this is a barrierless reaction. So the reaction should proceed basically at the diffusion limit. So this is an indirect way to measure the H atom diffusion within solid parahydrogen. And then about 10 years later, Uwe et al. Found that HF also appears to quantum diffuse in solid parahydrogen. And this was quite surprising. Basically, they do the same sort of thing where they make a HF doped parahydrogen solid and then just take repeated spectra and watch the HF molecules cluster or agglomerate. And thereby, this type of reaction, agglomeration reaction, is also barrierless. So you can also get an idea on the HF diffusion coefficient. And then finally, 5 years later, Momose's group reported that water also quantum diffuses. So I think the basic fundamentals of this quantum diffusion process are still not understood. And so that's one of the things my group is trying to look at. So we went back to an old favorite. So back in 2006, my graduate student, Paul Raston, at the time, did a lot of work on molecular chlorine. So that's the first species we're going to look at to see if chlorine atoms diffuse, quantum diffuse in solid parahydrogen. So here's the basic experimental setup. We deposit molecular chlorine in solid parahydrogen. We then come in with a 193 nanometer laser and photodissociate the molecular chlorine into 2 chlorine atoms. And I think if you looked at this, you'd say, well, you're just going to drive the reaction to make HCl and an H atom. But that's not the case. Look what happens. So if I look at the available energy to the fragments, the photon energy minus the dissociation energy, and then I take into account that the molecular chlorine will fragment into 2 chlorine atoms. So I distribute that available energy, about half goes to each chlorine atom. So that drops me down to about 3,700 wave numbers, which again would be enough to go over the classical barrier to reaction. But you also have to take into account the kinematics of this reaction. So we have a very heavy chlorine atom colliding with a light H2 molecule. So when you do the ratio to figure out this, the translational energy in the center of mass frame, which is what matters for chemical reaction, you find that only 5.4% of the translational energy will be available to the reaction. And so what that does is that drops us down so that now the chlorine atom can't even overcome the endothermicity in this chemical reaction. So we have a beautiful thing, because basically what we can do is we can produce metastable chlorine atoms and they won't react with the parahydrogen host. Now, I show there is a nuance to this that Paul demonstrated in his thesis work. And I just take a figure from a recent review paper, a chapter by Suge and Lee, where they talked about this. And so here is the chemical reaction with ground vibrational state hydrogen that I've been talking about, and that's all consistent with what I've been saying. But what you have to worry about is this idea that the hydrogen gets vibrationally excited. And so the parahydrogen solid can absorb near-infrared radiation and excite the hydrogen molecule within the solid. And that excitation can hop around within the solid until it comes up to a chlorine atom and then induce the reaction. So in these studies, we're going to be careful not to expose our sample to near-infrared radiation because we just want to create the isolated chlorine atom. So here is the basic cartoon of our approach. We'll make what we call a double doped sample of, so we'll put molecular chlorine and carbon monoxide in solid parahydrogen. We'll then expose it to our 365 nanometer output of our UV LED and convert all the molecular chlorine into chlorine atoms. And then if those chlorine atoms can diffuse, they can diffuse through the solid until they hit a CO molecule and then react with CO according to this reaction right here, which is also barrierless and exothermic. So basically by monitoring the growth of ClCO, we can see if chlorine atoms are diffusing. Here's our experimental setup. And so here is then the output of one experiment. We Haven't done enough experiments yet, so these results are all preliminary. But up at the top here is the temperature log of our experiment. So we cool our substrate down to below, liquid helium temperatures. We then deposit the chemically doped matrix, and then we just take repeated FTIR scans until the helium runs out. This gray bar is where we photolyze the molecular chlorine to create chlorine atoms. And then we just take spectra. And what I want to show is that we see no evidence for growth until we anneal the crystal, until we raise the temperature of this as deposited crystal. And this annealing process of an as deposited crystal is an irreversible thing. So we think that the growth that occurs during annealing is not evidence of chlorine atom diffusion. And so we're going to repeat some of these experiments to better figure this out. But here's the idea. So when you use rapid vapor deposition to deposit your matrix, it's kind of like here you're looking at our barium fluoride substrate, and that's the first monolayer that goes down. Then you put another monolayer down, and these are the hexagonal planes, right? And then the next monolayer, depending on its articulation, will either create an FCC, a face-centered cubic, or a hexagonal closed pack crystal structure. So when you grow crystals using rapid vapor deposition, you make a mixture in the as deposited form of FCC and HCP crystallites. Then by raising the temperature to 4.3, you can convert that almost completely to HCP. And it's during this process that we see evidence of the chlorine atom diffusion. And that's not what we really call quantum diffusion, because we want it to be happening slowly at a fixed temperature. So we're going to have to do some more experiments. But what I want to point out to you is this system, which we're very excited about, and that's molecular oxygen in solid parahydrogen. So sort of similar to the chlorine experiments, if we put molecular oxygen in solid parahydrogen and photodissociate it at 193 nanometers, what we see is the production of two O triplet P atoms. And energetics dictate that you can only produce the triplet P oxygen atoms. And so very analogous to the chlorine system, the reaction of O triplet P with hydrogen to produce H and OH is endothermic. So if we do it under the right circumstances, we will not have the reaction, and we can create these isolated O triplet P atoms. But different than the chlorine is that the O triplet P atom, if it can diffuse through the hydrogen solid, can find unphotolized molecular oxygen and form ozone. And if you form ozone, then things can change a lot, because if you form enough ozone during photolysis, you can photolize ozone and create O singlet D. O singlet D can react with the hydrogen host to eventually make water and H atoms. And so in these studies, what we really paid a lot of attention to was not irradiating the sample long enough so that we create H atoms, because we only want to produce the oxygen atoms and not have the competing or more complicated system of O atoms and H atoms. And then I point out that this O2 in solid hydrogen was last studied in early 2000s by Apkarian, so we're in good company. So here are the results. Here are just some FTIR spectra in the region of the ozone nu3 vibrational mode. And what you can see is before we expose our sample to the UV radiation, we have obviously no ozone. Then this is the first infrared scan immediately after the laser has been fired. We have a little bit of ozone. And then you can see, more than 10 hours later, we continue to see growth in the ozone. And so what we do is we take these infrared spectra and transform them into kinetic plots. So each dot here is an individual spectrum. So again, no ozone. While we photolyze, we see growth in ozone. But then after the laser shut off for up to 10 hours afterwards, we see growth in this ozone. So this is the O atom quantum diffusion. And so what we can do is we can just fit this simple kinetics to an analytical equation, right, to extract the rate constant for this chemical reaction, which is essentially, if the reaction is diffusion limited, is therefore a measure of the diffusion coefficient of the O atom. And the student working on this, Ibrahim, did experiments both in these as deposited crystals that have these mixed FCC HCP crystal structures, and in fully annealed crystals where we've carefully annealed the sample and converted it completely to HCP crystals. And what we can do is when we fit the rate constants for this chemical reaction, you can see that the rate constant increases by more than a factor of 2 in the annealed crystal. We take this also as further evidence that this is so-called quantum diffusion. And so Ibrahim has worked hard on this, and we've done repeated measurements where we've measured the kinetics repeatedly in a number of experiments, and then we're just presenting the rate constants here at the end. So as I showed you in the as deposited crystal, we have the slowest chemical rate constant. In the annealed sample, it now increases by about over a factor of 2. And then in the annealed sample that is at a higher temperature, so 4 Kelvin instead of 2 Kelvin, we don't see a real increase to within our experimental precision in the observed rate constant. And so this is all in our minds consistent with this idea of quantum diffusion. And that's what I'm trying to symbolize or show you in this cartoon to the left, where I have the red sphere is an oxygen atom in a parahydrogen matrix. And this is the potential for the oxygen atom at that lattice site, and there's its lowest energy level. And then when it moves over, right, if it moves over and is exactly the same energy, that quantum process where you tunnel back and forth between those two positions is the most facile. And so that is what we think why when we anneal our crystals, we get higher oxygen reaction rate constants. All right, so I'll just summarize what I've told you today is that our preliminary experiments show that chlorine atoms do not readily quantum diffuse in solid parahydrogen, but that's still very preliminary, and so we're going to keep working on that. We have definitive proof that O atoms do diffuse in quantum in solid parahydrogen, which I think is interesting. We've seen an effect on crystal morphology, and that it's essentially temperature independent. And what we're working toward is trying to gear up to study other O atom reactions other than just O plus O2 to see if we can make this a sort of a general technique to study low temperature condensed phase bimolecular reactions of O atoms. And so I'll just conclude with highlighting the people that do the work in my group. So Ibrahim has done all the oxygen work. And An is a new student that is going into her second year, who helped with a lot of these measurements. And the rest are, well, Aaron is an older graduate student from the group, and the rest are undergrads. And I also like to acknowledge funding from the National Science Foundation. And with that, I'll stop and entertain any questions you might have. Thank you.
Ralph Kaiser.
Oh, hi, Dave. Nice talk. Only one question. Maybe I missed it. When you generate the oxygen atoms in the triplet state, you generate them with kinetic excess energy. But the diffusion, how you describe it, is a thermal process. But the kinetic excess energy, the oxygen atoms are not in thermal equilibrium with the surrounding matrix. So did I miss something, or can you explain this a little bit more?
Yeah.
You generate the oxygens in different J states. Does this affect your interpretation of the diffusion constants? Thanks.
Oh, yeah. So our thinking is that the photolysis produces, as I talked about, non-thermal oxygen atoms, but the parahydrogen, within the parahydrogen matrix, they very rapidly become thermalized. And the diffusion of the reaction studies that we're studying are on the order of hours. So what we do is we separate when we're photolysing the sample to when after photolysis is complete. And what we're studying is the after photolysis sort of diffusion. We don't have any information on the fine structures of the O atoms. I mean, that would be something that'd be interesting to pursue, but we don't have any way to measure that. I hope that answered your question.
Okay, Stefan Schlemmer.
Hi, David. Very nice talk. The diffusion constant would depend on the concentration of your oxygen because you only gave a time. So do you have a real idea of, what is the way they travel before they meet an O2 on the average?
Yeah, those are excellent questions. And at this point, we haven't conducted the studies enough to answer your question. So at this stage, we're just happy that we're able to measure these quantum diffusion of the O atom and look at the morphology and temperature effects. But another area, which the one that you point out, is as a function of concentration, because you're right that if they have to travel longer distances, it should slow down and that sort of thing. And so those are planned studies by Ibrahim, where we're now going to look at the O2 concentration dependence of all these sorts of things. But that takes a lot of time and it's kind of hard. But I think it's very interesting. And you're right, those are the natural next steps. So thank you.
Hello, Carolina Haupa here. Some time ago in Taiwan, we were studying reaction of molecular oxygen with some metal, like halogen substituted metal radicals. That time we could observe that we can achieve the same effect if we leave matrix just overnight and wait for the reaction as during the annealing. Is it possible that what you observe is actually both motion or like mobility of the oxygen atom and oxygen molecule? Because from our studies, apparently oxygen molecule is mobile.
Okay, yeah. Hello, Carolina. Yes. Whoa, we hadn't thought of that. So thanks for sharing that information with us. I'll have to talk with Ibrahim about that. I don't know how we'd be able to disentangle the two. Maybe if we study other chemical reactions, but thanks for that. Yeah, I wouldn't have thought that O2 diffuses through solid parahydrogen. So, there's still mysteries out there.
For sure, like it's mobile. That's what I can confirm.
Thank you.
Move on and thank our speaker.
Thanks.
Our final speaker for this session is Johan Lassac from Aix-Marseille University.
So hi everyone. I want first to thank the organizing committee for giving me the opportunity to speak tonight. So huge co-sonum to Georgie, Clara and Gabor. The work I want to talk to you about tonight is about the formation of complex organic molecule in space, and especially in solid phase of space, in interstellar ices. And I will focus about the mechanism of formation of these icons. So a bit of context first. Interstellar ices are found inside dense molecular clouds, as you can see one on this nice picture. These clouds are made of solid grains, 1% by mass, And basically the 99 other percents are lighter atoms and molecules containing carbon, nitrogen, oxygen, and of course hydrogen, the most abundant one. And as the temperature of the cloud is really cold, down to 10 Kelvin, these atoms and molecules can accrete onto the grains, forming icy mantles. So that's what we call interstellar ices. These objects are pretty well known thanks to infrared observations. And as you can see, we have as main constituents here, mainly H2O, water, and some other small molecules like CO, CO2, methanol, and so on. Eventually, somewhere inside the cloud, there is dense part enough to collapse under its own gravity. It will form a protostar and a star that will emit radiation. This radiation will ultimately impact the interstellar ices, and through radical chemistry can form larger molecules. Then the star will continue to evolve, hitting its environments that will, at some point, sublimate, the ice, releasing the molecule into the gas phase, where they can be observed through rotational spectroscopy. And there can be also a solid residue on the grain. Speaking about observation of these species in gas phase, to date we have about 270 different molecules that were detected. Glycolaldehyde, methylformate, acetaldehyde are 3 examples. So we know that to form this molecule we need a combination of solid phase chemistry, radical chemistry, and a lot of gas phase reaction as well, as we saw with some interesting talks in the conference already. And we also need energetic processes. But what we don't know much about is what happened in the middle, that is to say the precise formation routes of these molecules. So the question I want to give some answers to tonight is how to determine reaction mechanisms, and we'll give an experimental point of view, focusing on the methanol photolysis, as it is a relevant precursor that we observe in interstellar ices. So basically, I will try to characterize some radicals formed by the photolysis of methanol, and then see how these radicals can recombine together. And the side question that we can ask is, does the reaction A plus B always give the AB product or not? So to do this, I use 2 experimental setups. So the first one is ring in Marseille using infrared and QMS techniques. And the other one is a collaboration with Dr. Wolfram Sonder that allows us to do EPR, electron paramagnetic resonance. You have here a photo of ring, so you can see in the front the 2 techniques, infrared and mass spectrometry. We have here the mixing ramp, and of course the central part of the experiment is the cryostats with the sample holder that we can cool down to 10 Kelvin, 11 Kelvin, allowing us to deposit gas phase molecule to form ice analogs onto it. Then we can monitor these ice analogs using VUV photons, Lyman alpha photons, to generate radicals and products. And of course we can monitor the evolution of the sample in situ using FTIR. And secondly, what we do is we increase the temperature of the sample holder up to ambient temperature so that we will trigger desorption of this molecule to the gas phase of the chamber. You can basically collect this molecule using the mass spectrometer. And here we have 2 methods of characterizing molecule. First one is we separate them using the characteristic temperature of desorption. And secondly, we can also, as we use electron impact, we can also have a different pattern of fragmentation of these molecules that allow us to add some clues about the identification. Here you have some photos of Bohr experiments. You can see the magnets, and in the middle the microwave cavity. You have also a nice view of the sample holder there. It is basically the same kind of experiment as ring, but instead of having infrared and mass spectrometry, what we use is EPR. So this technique is really specified into the detection of paramagnetic species. So in our case, it will be only radicals. We will not detect any reactants and not any products. So we see only the intermediate species. So it makes it easier to see them. And also it's a really sensitive technique. So you have here an example of spectrum obtained when we photolyze methanol inside an argon matrix. We arrive to the main question, that is how to determine reaction pathway in interstellar ices. So before to answer this, let me just show you some results about what we obtain when photolyzing a relevant ice composed of water, methanol, and ammonia. That's a work done by Grégoire Dinger, a colleague of mine. And when he photolyzed this sample, he obtained a solid residue that he can characterize using high-resolution mass spectrometry. He obtained this spectrum composed of thousands of peaks, so potentially thousands of products, as each peak is one molecular formula. So it's really interesting work in terms of complexity and diversity that we can see in interstellar ices, but obviously in our case, it will not help us to determine any kind of mechanism because there are too many channels. So what we need to do is to simplify this ice analog. We did it by two ways. First way is to remove one of the partners, that is NH3, so that we have one atom less, one partner less. We reduce a lot the quantity of reaction channels. And the second way is that we replace the reactive H2O matrix by an inert gas, that is argon, to create what we call a cryogenic matrix isolation of methanol. So a few words there, we use a 1/1000 ratio so that we minimize the quantity of dimers. We want to have only monomers of methanol. And then when we photolyze this methanol with UV photons, we obtain intermediate species that are radicals, that are isolated one from another. They can diffuse, they can react together, so their lifetime is greatly increased so that it's easier to characterize them using infrared and EPR. And also there are ground states because they have time to relax within the matrix. The next step is we make dissolve the argon matrix by increasing the temperature to 35 K, so that now we don't have anymore the cages that separate the radicals, so they will diffuse into the solid film that is forming to form stable products that we can characterize using infrared and QMS, just as I told you with the presentation of ring. Of course, we do a lot of isotopology experiments also to confirm each attribution. And the final thing that we got is a complete scheme of the reaction, starting from the reactants, going through the products, and we have also the detection of intermediate species that allow us to speak about mechanisms. What are the results for this study? So I show you here two spectra, one infrared detection one to the left and one EPR detection one to the right. Just to tell you that these two techniques are here complementary. We can use both to confirm some radicals that we form, such as HCO, CH2OH, for example, but we can also use them to have information of some radicals that we can only see using infrared and other only see using EPR. A nice example is the formation of CH3 radical that we can observe in infrared using these three bands there that we don't see using EPR. And the reverse is also true, as we have indication of CH3 and OH radical there in EPR that we don't have in infrared detection. At the end, we got 7 different radicals, and what we want to do now is to test every single recombination of this radical with themselves and with the others. So it makes us draw a double entry table. Each single case of this table represents a stable product by the recombination of 2 radicals. So for example, if I take the line of HCO and the column of CH3, I end up with acetaldehyde. If I move one column to the right, I end up with glycolaldehyde. And to put some relevance into the study, I will show you there by order of chronology all the species that were already detected in the ISM. So you see that it represents most of the table of these molecules that we are studying. So I will keep a white square to mark them. And our results are these green molecules that we effectively detected using our experimental setup. So it's interesting, we see most of them, but maybe most interestingly, we don't see some of them, the red one, telling us that the radical plus radical reactivity is not always working for these molecules, at least. So, and especially for the acetaldehyde case, that it is a molecule usually detected in the ISM, we don't form it in our experiments. So the question is why we see we don't see acetaldehyde and we see glycolaldehyde. So we can take this theoretical work done by Enrique Romero, when he showed that in a cluster of water, the HCO plus CH2OH is effectively working to give glycolaldehyde, but HCO plus CH3 does not work and does not lead to acetaldehyde, because there is another reaction pathway that is highly preferred, that is the H abstraction of HCO to give CO and methane. So that's probably what we obtained also in our experiment for all these 3 red molecules. And finally, for the yellow one, we were not able to conclude for some reasons. Some of these molecules, we could just not see them because our setup was not designed for. For example, H2, we begin the TPD at high temperature, so we were not able to see it. But for most of them, the reason was that we didn't have enough spectroscopical evidence from the literature to interpret our results. So that's specifically the case of the acids. That's why we are currently working on a specific experiments to fill this gap about the acid. And my poster is about this, so if you want to come to talk with me about this, you're welcome. As concluding remark, to answer the main question, we propose a solution that is to combine some techniques. So the classical ones, FTIR and QMS-TPD, of course, but we propose to add EPR spectroscopy as an additional technique that is perfect to see the intermediary species. And of course, cryogenic matrix isolation that allow to control the reactivity step by step at low temperature. And yeah, to control the reactivity and to be able to speak about mechanism more easily. About the result, we saw that photolyzing methanol, we get 7 different radicals. Most of the recombination work at 35K, and I put a warning there, it works at 35K because the desorption temperature of argon, when the radical can meet, it's 35K, and we didn't test lower temperature. But maybe more interestingly, some recombination do not work, meaning really that radical plus radical reactivity is not always a straightforward mechanism to think about in interstellar ices. There are sometimes other kind of mechanisms. That's why we are currently working about this other kind of mechanism. And I have also great results about a new pathway for glycolidate formation in solid phase, going from HCO plus H2CO reaction. And to finish, of course, the next step is to apply this methodology to more relevant ices composed of water. So that's basically the subject of my poster. So if you didn't come to see it yesterday, yeah, please come to see it when you have time. We'll discuss about this. I want to end this presentation by thanking all the persons and institutions that allow me to present you this work today, especially Dr. Fabrice Duvernay and Alejandro Gutierrez Quintanilla. And of course, all of you for your kind attention. Yeah, thank you.
Thank you for a very interesting talk. I have one comment and one question. Actually, I strongly doubt about EPR detection of OH radical in an argon matrix, because it is well known that it is orbital degenerated species. It means very strong anisotropy of G factor, and for 50 years it was proved many times that it can be seen only if this degeneracy is lifted due to strong interaction, like in water ices, on complexes, and something like this. So I just suppose that you consider carefully, do you really observe OH radical? Because the line should be severely broadened, like for methoxy radical. It's a comment. And the question is, I did not catch, how can you get HOCO radical? You need second oxygen atom. Where it comes from?
Yeah, thank you for your comment and your question. Just for your comment, you're right. We observe a broad signal that maybe we can attribute to OH radical. And that's why we use also 2 techniques, infrared also, because we have some weak bonds for the OH radicals that can confirm the presence of the radical. And for HOCO, that's a really good remark. What happens is, using the EPR setup, the background pressure is not good enough so that we have a lot of CO2 contamination. So we think that using this EPR measurement, we are in fact probing the CO2 plus H reaction that form HOCO. But in case of the infrared detection, we see it only after annealing. Okay, so we photolyze at low temperature. We don't get any HOCO because, as you said, we need 2 O atoms and we don't have any dimers of methanol, so we can't have these 2 O oxygen atom close. But we did this annealing at 30K that allows some species to move, like CO, for example, and then we get some HOCO that is produced.
Or trans HOCO. There are 2 isomers. Do you know which one it is?
Yeah, it appears that from the literature, the value that we took for the parameters correspond to the trans HOCO only.
And the last question of the session will come from Ralph Kaiser.
Thank you. Can you please go to the slides where you mentioned that the acetaldehyde is not formed?
Yeah. This one.
No, this not one.
Okay.
Back.
Okay, I guess this one.
Yeah, this one. I doubt that this is the right conclusion. First of all, it's well known that acetaldehyde can be formed by reaction of HCO radical recombination BCH3 even at 5K. This is really well established because we did it. Okay, sounds strange, but it's true. And secondly, the reason why you don't see acetaldehyde in your experiment is because the infrared absorptions of acetaldehyde overlap with the infrared absorptions of the more complex molecules which you have. So you simply cannot see it, but you have it. In particular, the carbonyl functional groups, it's overlapped by the glucolaldehyde and by other molecules which have a CO functional group. So that's one of the suggestions when interpreting IR data of complex molecules. It doesn't always give the truth.
Yeah, I was waiting for this comment. Thank you. In fact, you're right. We can't see it using infrared, but that's why we use afterwards mass spectrometry, and we know precisely where to find acetaldehyde in mass spectrometry, and we didn't find it using either the 12 carbon isotopologue and the 13 one. So that's the reason why we state that we don't observe this. Yeah, no, but you can read the article if you want to. We are pretty sure about this non-attribution. And what I wanted to say is that maybe the reason why you see acetaldehyde, I think, is because of your environment. Here we are working in matrix, so we have only first-order products that can be formed because we generate the radicals and then we allow them to react. In your case, maybe you are in like a more complex environment, water, or I don't know which one. So you can create complex molecules that are then photolyzed as well and can form other molecules. So what we think is that, in fact, acetaldehyde will come from the photolysis of ethanol, rather. And we have some other experimental proof of this. I'll let you check the Grégoire Danger et al. That will come soon. He has some experimental proof about this mechanism also. Thank you.
So actually I lied and I was told there's an online question.
Yes, this question comes from Sergio Iopolo. Hi, Johan. When you apply EPR to ice experiments, I assume it's done by using a different chamber compared to the analog experiments with FTIR and QMS. If so, do you have a good control on experimental parameters across different setups? Are the conditions the same in all cases? How reproducible can your experiments be?
Yeah, thank you a lot, Mr. Iopolo, for this question. Yeah, actually, as I said, the background pressure is not the same, and of course we use 2 different setups there, but that was on purpose for making this paper that is a proof of concept. And now we just receive a grant to buy our own apparatus. So we receive the X-band magnet in our lab, and we are currently building the setup that will allow us to do in the same exact condition infrared and EPR.
Let's thank all of our speakers. So the talks are done, but if you look at your program, the session actually goes on until 2 a.m. And I'll now turn it over to Yuri.
Yeah, I hope it will be quick, but we have to renew the International Scientific Committee. We have two kinds of members in the committee: those who organized the previous meeting, the present, and the future meeting. So David Anderson Jay, don't go away because I want to nominate you. Okay, so sorry. So David will step down, and hopefully, if he drinks enough, then Chris Merton will step on, hopefully, for 2026. We hope. Okay, we will see, but we will try to convince him. Okay, and Naoki will be the chair of the next meeting in Japan, and I will be in the committee as the past organizer, past chair. So the other members are Stefan Cusso, Vladimir Feldman, Wolfgang Jäger, Robert McMahon, Joel Massetti, Sonia Melandri, Igor Reva, Sebastian Riedel, Tatiana Sabatina, Andrei Vilesov, Klaus von Heften, and Tomonari Wakabayashi. And we have to replace the members who were elected a long time ago, namely Joel, Robert McMahon, Andrei Vilesov, and Tatiana Sabatina. So we have to elect 4 new members, and the scientific committee nominated two names. One of them is Vutrat Chin, and yeah, just come here, and Takamasa Momose. They accepted the nominations. So if you want to say some words.
Hi everyone, that's the third time you see me today, sorry. Well, I've already spoken today, but well, very briefly. So I am a researcher at Orsay, Paris-Saclay University. This is in the south of Paris, France. And my interests are in, of course, matrix isolation spectroscopy, as I showed today. So I use infrared spectroscopy, UV spectroscopy as well. And I'm essentially interested in hydrogen-bonded molecules. And there is another part of my research activities who are a bit far away from the CPLT community, and it is more related to time-resolved infrared spectroscopy, which is a technique that is based on nonlinear optics. Right. Thank you.
Thank you. Taka, are you online or not? You see online? Okay, and still both Rob and Andre from US. Probably it would be nice to nominate somebody from the US. So I thought that Jay used to come to these meetings very frequently, so I would like to nominate you for. Do you accept the nomination? Yes. Do you want to say some words?
Yeah, my name's Jay McAngelo. I'm a faculty member at Penn State, Erie, which is an undergraduate campus of Penn State. I do matrix isolation. My own lab, I do mainly argon and nitrogen matrices, but I also have done some sabbaticals with YP Lee, so I've done parahydrogen work in his lab. In my own research, I do mainly complexes, intermolecular complexes, but we also do some studies of radicals and things like that. So.
Okay, so we need, for an election, we need at least 5 names. We have 3, so any other suggestions? Self-nominations, nominations? Ralph? Do you want to work? You like to work? Do you want to work for this community? Okay, so you want to run for the election? Okay. And at least one more name from Germany. A young researcher, Aaron Bochum. Okay, so now we have 5 names. You? Do you also want to run for the election? Yeah. Okay, then we have 6 names. It was very democratic. Okay, but we will have the election. Okay, so we have 6 names, and we will send out the how to vote. It will be the same like we voted for the Pimentel Prize. We will use the same system. If you had any problem with that system, please report it to Gabor right now. And we will send out the letters tomorrow morning, I think, because, okay, you can choose the 6 names, you have to order you have to make your preference. Okay, thank you very much.
I have to make an announcement about the hike, not to those of you who are coming, because I sent a message to those of you who are not coming. Keep us in good memory. But no, if you are living in the other hotel,